Now we're going to talk about parallelism in the memory hierarchy, and in particular cache coherency. So let's take a look at the example we've been seeing before with what happens when we add caches to it. So now we're going to put caches in here. So each processor has its own cache. And what happens? Well, processor 1 goes ahead and loads the balance. Now the balance gets stored in the cache, and you can see we've got our flag bits here, so it's valid and it's not dirty. Processor 1 now has 510 as its balance. It checks the balance, it goes ahead and updates it, it writes the new balance back to the cache. You can see it's valid, but now this data is dirty because it's been updated in the cache, and it goes ahead and finishes. But the DRAM value is still 510 here. So even though this processor 1 has completed here, the DRAM still thinks the value of balance is 510, and that's because we've only written back to the cache. The data from the cache hasn't been updated into the DRAM. Now processor 2 comes along, and it's waited until processor 1 is all done. So we don't have the synchronization issue we had before here. Processor 2 is waited. Processor 2 now loads the value from DRAM, and it gets the old value from DRAM, because it's still only 510 in the DRAM. It goes ahead and starts doing its processing, it stores back, and now it's got its cache line saying the new balance should be 310, and it's got the dirty bit set, and it's done. So what happened here? We have three different values for the balance variable in the system. We have one in cache 1, which is the result of processor 1 running, one in the DRAM, which is what we had from the beginning, and one in cache 2, which is the result of processor 2 running. This obviously isn't what we want. So what is the problem here? Well, the problem is that the caches didn't communicate with each other to know when they have to update the DRAM. There was no way for cache 2 to know over here that when it went to get the data from here that there was a newer value in cache 1. What we need for some way for cache 2, when it tries to access this data, to tell cache 1, you better go ahead and update the data in the DRAM so I get the right value. So what's the problem we have? We have multiple processors, and they each have their own caches. When they bring data into their cache, they get the latest value from DRAM, but there may be newer versions in other caches. And how do we find that out? And this is called coherency. This is the idea that we need to keep track of who has the latest data, so we make sure whichever processor we're at and whichever cache has the latest data, we always get the most recent version. One solution to this is called snooping. So in snooping, each cache is going to listen to what the other caches are doing. And we do this by connecting the address wires between the cache buses all together. So we connect them together, and now every cache can listen to what every other cache is doing. If a cache sees another processor write to a line it has, then it invalidates its line, because it knows the other processor has updated it, and so it's going to have to go get new data for that. If it sees another processor trying to access data that it has that's dirty, it knows it needs to write that data back to the DRAM so the other processor gets the right data. So let's take a look at this. So here's our example, and we're going to use snooping. So processor 1 goes in, it's going to load the balance. Balance gets copied into the cache. It has 510, it goes ahead and does the computation. Now its cache has a balance of 10 and it's dirty. The DRAM, however, still has 510. Now processor 2 is going to go ahead and load its balance. But when it goes to load the balance, what happens is this snooping. So cache 1 snoops on this transaction. It sees what cache 2 is trying to do and says, wait a second, I have this balance variable and it's dirty, so cache 2 over here, you need to wait for me to write it back. So this read doesn't happen. Cache 1 goes ahead, takes its dirty value here, writes it back to the DRAM. Now that it's written back to the DRAM, now processor 2 can go ahead and read it, and it will read the correct value. So now processor 2 gets 10 as it's supposed to. You'll notice over here in cache 1 has now written the data back to DRAM. So this line is no longer dirty, and it's unset the dirty bit. Now we can go ahead and execute the program, and we're all done. So how did snooping help in this case? Well, snooping allowed cache 1 to tell cache 2 that it had newer data and make it wait for it. By snooping on the data that cache 2 was using, cache 1 could tell that it had to update the data in the DRAM, so cache 2 got the right data. So what is snooping? The idea in snooping is that all of the caches listen to see what other caches are doing. If a cache writes new data, we need to invalidate our data locally so that we know that we have new data somewhere else. If a cache reads data that we have, we know that we need to update the data in the DRAM if it's dirty and tell the other cache to wait for that data. The way this is implemented is by tracking the cache line state. So just like we have valid and dirty bits, we're going to add extra bits for tracking it. So we add a modified bit. A modified bit means I have the data in my cache, but I haven't written it back to DRAM. This is basically the dirty bit, but it's a dirty bit if you have multiple caches. We have a shared bit. This means the data is the same as the data in the DRAM, but multiple caches may have a copy of it. And then we have invalid, and this just says the data I have isn't the right data and you have to go get it from DRAM. So let's take a look at an example. Say cache 1 and cache 2 both have line X and it's both shared. So it's shared, that means both of them have the same data that's in the DRAM. Now cache 2 writes to line X. So now it's no longer the same as the DRAM. So cache 2 is going to change this line from shared to modified because it's changed it. At the same time, cache 1 is going to change its line to invalid because cache 2 has now updated the line and cache 1 doesn't have the right value. Now if cache 1 wants to read the line in, cache 2 sees the read by snooping, writes the data back to DRAM, and changes it to shared because it's now the same as DRAM, and then cache 1 can read in the line and mark it as shared because it's the same as the DRAM. So to do this coherency right, you have to keep track of these states and when you change them, and this is tricky. So to summarize coherency, we have multiple caches. That means we can have multiple copies of data. Coherency keeps them all synchronized to make sure we get the latest version. We implement coherency by keeping extra bits around for shared, modified, and invalid, just like we did for valid and dirty. All of the caches need to watch what all the other caches are doing to make sure everyone has the latest version of the data, so this is tricky. And putting it all together and making it right is really hard. This is actually one area where computer architects have turned to other people to say, can you prove that our coherency thing is right, because it's too complicated for us to test everything. So a question on snooping. What did cache 1 do when it saw that cache 2 was trying to load the data it had? So what it did was it wrote the data back to DRAM and told cache 2 to wait. So cache 1 saw that cache 2 wanted data it had that was dirty. So first it wrote the dirty data back to the DRAM, and then it told cache 2 that now it could get the data from the DRAM. This made sure that cache 2 got the right data. Here's a question. If cache 1 has a line that is modified, and cache 2 tries to load that line from DRAM, what does cache 1 need to do? So in this case, cache 1 needs to write the line to DRAM, clear its own dirty bit, and tell cache 2. So cache 1 sees that cache 2 wants the data it's modified, needs to make sure that it puts the data into DRAM and tells cache 2 that it can get the data from DRAM, and it also needs to clear its dirty bit, because once it's put the data back into DRAM, that data is no longer dirty.